Okay, what I'm going to do now is I'm going to run through an example problem that we would work with in this NMR course. And in this problem I'll provide the molecular formula, which I've shown is C8H10O2, and I'll provide the spectra for it, so the carbon-13, the proton spectra, and maybe I'll provide IR as well. And what we've got to do is we've got to try and piece together exactly the structure of this molecule we have. So the first thing I would do in trying to solve this problem is, before even looking at spectra, I would calculate the double bond equivalence. So please use the formula for double bond equivalence to calculate what the double bond equivalence is for this molecule, and you should get the answer 4, which means that we've got 4 double bonds, or 1 ring and 3 double bonds, or 2 rings and 2 double bonds, etc. It's a very good idea to know this before you start. Bear in mind that if you've got a benzene ring, it will have a dBe of 4. A benzene ring is a ring and 3 double bonds. So already at this point I'm suspicious that there may be an aromatic part to this molecule that is giving rise to the double bond equivalence of 4 that I see here. Of course, that might not be the case. We might have several double bonds and carbonyls, etc. But my suspicion at this stage is that we may have an aromatic system because its double bond equivalence is 4. Okay. The second thing that you need to do is you need to just briefly look at the NMR, the proton NMR spectrum, and just check the integration, these numbers over here. We need to check that the total here matches the total we have in our spectrum. If we find this total comes to half of what we've got in our molecular formula, we know then we have to double up. And it's important to do that so that we know precisely how many protons are giving rise to each signal in the proton NMR spectrum. So if you count this, you will notice that that's 4, and that's 6, and that comes to 10, that matches exactly the number of protons we've got in our molecular formula. So these numbers are perfectly correct. The 2, 2, 2, 3, 1 are correct. So this is important as we carry on. Okay. Then you've got to do the same thing in the carbon spectrum. Just check that the number of carbons you see matches. So we should have 8 carbons here. There's no solvent signal for us to worry about, but let's have a look at the remaining signals. We've got 1, 2, 3, 4, 5, 6. So we are missing 2 carbons in the carbon-13 spectrum. That means that 2 carbons are overlapping, and the most likely suspects are the more intense signals. And so you can see here that it is quite likely that we have overlap at this point and overlap at this point. So the doublet, the CH here and the CH here are where we are overlapping. So this signal is going to be 2 CHs, a CH and another CH, and that will be a CH and another CH as carbons in the carbon-13 spectrum. And then we've got some quaternary carbons and some other signals floating around. So 2 must be overlapping. Okay, and so these are our likely suspects. Of course, if something goes wrong, we may have to think very carefully and revise this decision, but at the moment I've identified those 2 as being the overlapping signals. Okay, right. So one other piece of information we can work with is we've got the depth information, we've got the multiplicity here. So we can count how many protons that accounts for. So for example, we know this Q is a CH3, which means that in the carbon we've got information about 3 hydrogens. Over here it's a CH2, so we've got information about 2 hydrogens. So it's interesting that this carbon-13 spectrum is going to show how many hydrogens are attached to carbon in this molecule. And if we count them, you'll see that there are 3, 4, 5. Remember, this is doubling up. 6, 7, 8, 9, and there are no hydrogens attached here. So this spectrum shows that there are 9 protons attached to carbon in the molecule. That we're missing 1 proton. The proton we are missing is not attached to carbon. It must be attached to something else. And if you look at the molecular formula, the only other thing it can be attached to is an oxygen. So we must have an OH in this molecule. Okay, so only 9 atoms are attached to carbon. The remaining hydrogen must be attached to O. Count up these hydrogens that I've placed here due to the multiplicity information and confirm with yourself that there are 9. Note that this matches the infrared information, and you can see in the infrared that there's no strong band for the carbonyl, but there is this broad band for the OH, and so we've confirmed that we have an OH in this molecule. Right. Now, check for double bonds or aromatic. If you look towards the left of a spectrum, it's easier to interpret what's going on by looking at the left of the spectrum. I notice in this case that we have got some signals around about 7, and signals around about 7 are aromatic signals. So my first suspicion is that I have a benzene ring, and of course by looking at the integration I note that we have 4 protons in the aromatic region, which means that we can draw an aromatic system with 4 protons around. But to get the splitting, to get the doublets, and to get the overlapping, the only substitution on the ring that we can have is a parasubstituted system, so that we have an identical H and an identical H in this case that will overlap, but each of these have 1 neighbor, so that will all be doublets. So this pair will be overlapping doublets, and this pair will be overlapping doublets, which is what you see over here. The only way for them to arrange, if you have any other way, if you were to move this hydrogen here, you might have an isolated hydrogen which is a singlet, which will not match this at all. If you put this hydrogen here next to this one will then have 2 neighbors, and you'll end up with a triplet. So you can't move the hydrogens around away from this arrangement to get this splitting pattern that you see in the aromatic region. So we've got to have a parasubstituted benzene in this. Okay. So just check in the carbon spectrum that this matches, and that's absolutely correct. It does work because we've got these 2 quaternaries that work nicely, and of course the overlapping works fantastically. This CH overlaps with the CH that we saw before, and the CH overlaps with the CH which we saw before. So this arrangement of benzene substitution matches in the carbon-13 spectrum, and we've identified that all these signals here, all these deshielded signals here, are from the aromatic system. Right. Now we need to have a look and see what H's are coupled and which are isolated, and it's really interesting to see that we have a methyl group here and we have a CH2 group over here, and they are both singlets. So they cannot have any proton neighbors. So just be aware, we've already sorted out the aromatic region, we know about neighbors here, but notice that these have no neighbors here. And of course the signal that integrates to 1, it's only one thing that integrates to 1, and that has to be the OH. If you have a look at your carbon, note you've got your CH3 and your CH2. There's no CHs here, So the only thing that integrates to 1 has to be the OH that we found. Okay, so please be aware that your CH3 and your CH2 are isolated. We cannot, when we piece the molecule together, we cannot place them next to each other, or else we are going to get splitting in the spectrum, and so the answer will be incorrect. We've already identified splitting on the aromatic system, so we don't need to worry about it further. Okay. Check that you have all the pieces, and you've got to check that they all match the molecular formula. If you put together our aromatic system with our 4 hydrogens, our CH3, CH2 and OH, you'll see that we've got the right number of carbons, we've got the right number of hydrogens, but we don't have the right number of oxygens. We find that we are missing another oxygen. So we've got to place that piece on the table, because otherwise, if we try and piece the molecule together without it, we're not going to match our molecular formula. Right, now we need to put them together. Now, if you put these, there is more than one way to put these pieces together. Note that if you try and put them together like this, with the CH2 next to the CH3, your answer is going to be wrong, because should you place them next to each other, in the proton spectra, you should get splitting. We see no splitting in the proton spectra, so they've got to be isolated. So when you put the molecule together, the most important thing is that you have got to isolate those from each other. So here is one possible way that you can place it, where your CH2 is on one side of your aromatic system and your CH3 is on the other side. Or you could have them on the same side but separated by an oxygen. That would ensure that your CH2 remains a singlet and your CH3 remains a singlet. So both of these possibilities are correct. We would need further information beyond NMR to determine which of these is exactly the correct piece. But please, in all cases, make sure that your pieces add up to the molecular formula before you try and piece them together. If you do not have the complete picture of C8H10O2, there's no way that you can get a correct answer for the spectrum. Finally, check back against the spectra, does it work? And you'll find that both of these are consistent with the spectra we have available. Just double check that we have a methyl group, CH2, overlapping CH, 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 quaternaries, yes, that matches. Do we have an OH? Yes, we've got an OH in both cases. Do we have a CH3? Yes, CH2, and the substitution on the aromatic system. Okay, so always check back against the spectra, and most importantly, check that your compound, your proposed structure, matches the molecular formula.